going to look at some combined infrared and mass spectrometry questions today. We occasionally get one of these. In fact, they're quite common on the old specification, the new specification. There's been one already on the 2016 paper, which is available online. So if you want to follow me with this, you need to find the 2016 depth paper from OCR, Chemistry A-level, and it's question 7. So here it is, and the first thing we're going to do is we're going to read through it without thinking about it too much, and then I'm going to read through it again, and everything that I find I'm going to draw out and flesh out into my answer space. So, organic compound C has the following percentage composition by mass. We have an empirical formula to work out there, obviously. The infrared spectrum and mass spectrum of C are shown below. There's an infrared, there's a mass spectrum, fantastic. Already I can see that this has got some characteristic peaks in it, and I've got an M+ ion up there, which I can use to work out what the molecule is. This is important. In the mass spectrum, a secondary carbocation is responsible for the peak with the greatest relative intensity. Identify compound C. In your answer, you should make clear how your conclusion is linked to all the evidence. So the first thing that we notice here is that we've got this question here, is an extended response question, so it's going to be marked in terms of levels. This means that we've got to make sure that we include absolutely everything, because the only way we're going to get the top level of the marks here is if we've mentioned everything the examiner is looking for. Okay, so what might that be? Well, the clue's in the question. So here I've got some percentages with elements. If we've got an elemental percentage, we can work out an empirical formula. So I've got carbon, hydrogen, and oxygen, and I've got 54.5% of that, I've got 9.1% of that, I've got 36.4% of that. If I've got a percent, then if we say I had 100 grams of it, then I would actually have 54.5 grams, 9.1 grams and 36.4 grams. If we have a mass, and we look on the periodic table for a relative mass, we can calculate the number of moles. So I'm going to take the relative mass of carbon as 12.0. I'm going to take hydrogen as 1.0 and oxygen as 16.0 from a periodic table. And that will give me the number of moles. Now notice I'm doing this in columns. I'm doing that for a reason. It keeps everything nicely organised. So I know what's carbon, I know what's hydrogen, I know what's oxygen. So the carbon works out on my calculator as 4.5416 recurring. So I'm going to do that to just 2 decimal places there, because this is going to be 9.1. I can already see what the ratio is supposed to be between those two, because that's roughly double that. And then the third one, if I put that through my calculator as well, I get 2.275. Let's just do it to 2 decimal places, why not? Okay, so we end up with 2.28 for that one. And again, you can see that actually if we multiply that by 2, we get this one as well. So what we're saying here is our ratio is this to this to this, and therefore if that's the smallest one, that's a 1. This is roughly double that. If you could put it through your calculator, it turns out as pretty much 2. And then this one, if you take this one and multiply it 4 times, you get pretty much that. So that's 1 to 4 to 2 is our whole number ratio of moles. Okay, and that ends up with our empirical formula as C2H4O. Now it's important to write in empirical formula equals that, because with that it makes it clear communication. This is what this means. This means that this must be our empirical formula. Now that's the simplest ratio of atoms that we could have. So where can we go with this? Well, where we can go with this is we can look at the mass spectrum, and we can use the mass spectrum to work out whether that empirical formula is the same or as a molecular formula, or whether there are in fact multiple units of that in the formula. Here then is my mass spec. What do we notice? Well, first of all, our empirical formula was C2H4O, which if you add up 12 times 2 plus 4 plus 16, that actually gets 44. So if we look at 44, there's obviously more stuff which is much larger than that there. So the question is, what's our M plus peak? And our M plus peak here, our molecular ion is going to be here. It's going to be this large one, not this small one. That's the M plus 1 peak, which is caused by carbon-13 isotopes in the sample. Okay, and you can tell that because this one is diddy and this one is much, much clearer. So I'm going to write M plus peak equals 88 M over Z. MR equals 88 grams per mole. Okay, so empirical formula equals 44 grams per mole relative mass. 44 times 2 equals 88. Now I'm putting that in. You've got to put that in because we're going to link this empirical formula here with this relative mass here. We've got to say that it's 2 times the empirical formula. That's got to be written in here. Okay, so molecular formula equals C4H8O2. So now we know what the formula is. There are lots of different compounds that we could guess that was, but there's a bit more information here. There's the infrared. So let's have a look at the infrared. Here it is. There are 2 things that we can see here. You should have learnt some characteristic absorptions and to recognise them. Now we could examine this fingerprint region here. We could examine this bit here as well. We could see what on earth is going on in all of that. But actually the important thing here is that we have 2 very distinct peaks. We have this one here at 1700 and we have this one here at 2500 to 3300. Okay, and we know that things which appear here and here are going to be caused by carbon to oxygen double bonds for this one, and probably O to H single bonds here. And because it's broad here, we know that we're going to have probably an OH rather than anything else, which is going to turn up here. We've got some CH bonds here, there's some COs down here, but they're not important. The telltale thing for this is the OH and the C to double bond O functional groups. So in infrared spectroscopy shows peak at. Now what I'm going to do here is I'm going to look at my data sheet and I'm going to write down the exact number which is on the data sheet. So it's a peak at 1630 to 1820 centimeters to the -1 is caused by a C to double bond O. So a CO double bond is what I mean there. And then I'm going to go peak at 2500 to 3300 centimeters to the -1 is caused by an OH bond. Now there are 2 OH bonds that we could turn up there, and this is really important. If you have a look at your data sheet, you'll notice that there's one which could turn up at 3200 to 3600. Now if we have a look on this one, you can see that if we compare them, that we've got between here and here is what I've said, which means that the vast majority of all of this is in that range. Now if I went 3,200, that would start here, and 3,600 would start here. You can see that actually there is a bit of the peak in there, but it's actually in the wrong place. So we are here, not here. And that's important because that tells us that this is a carboxylic acid. Therefore, this is a COOH functional group. In the mass spectrum, a secondary carbocation is responsible for the peak with the greatest relative intensity. Now, they haven't just given you that to be helpful. They've given you that because they want you to tell them about it. So let's find out what that is. If we have a look at here, this one here is the one with the most intensity. So let's have a look. That would be 41, 2, 3. So that's M over Z 43. Okay. We know that it's going to be a secondary carbocation. So let's have a think about this. We know that a CH3 group equals 15. We know that a C2H5 group would be 14 more than that, which is 29. If we put on a third carbon atom, C3H7, we find that that actually equals 43. We've added another 14. Now, if you do a lot of these, you'll know 15, 29, 43 tend to be these carbocations. Now, remember there's a carboxylic acid in here. If we just had that, then that would be 45. And I've almost fallen into the trap that lots of people do, which is I've forgotten to put a plus on here. So let's put a plus on here because they are fragments. So here are some possible fragments. Now so we know it's not going to be the COOH. And actually, if we take the COOH and we take this one here, that would be our whole molecule, wouldn't it? Look, C3, and then one more is C4. We've got O2, then we've got H8. So these two fragments here would add up to 88, and therefore we probably have this one and this one joined together in the middle. So what's this one? That could be anything. We know that that is going to be secondary, and in order to make that into secondary, we could have this. We could have the plus here, or we could have the plus here. Secondary is here. So we're going to have a secondary carbocation like that. Now if that's the secondary carbocation, then the bond must have come from where that plus is. The bond that we've broken to fragment it was that bond where the plus is. So that means if we join that bond onto a carboxylic acid like that, we satisfy all our criteria. Look, if we break that bond, we get our secondary carbocation, this one. We have the CO, we have the OH. There's no other way that we could arrange these carbon atoms in order to get a secondary carbocation. And so there is our answer. Now, just to link this in a bit more, I'm now going to put peak with highest relative intensity is this. I know I've just said that there, but I'm going to be absolutely clear because I want to make sure that the examiner is absolutely sure what I'm saying here. I've already put the mass up here, so I don't see the need to repeat myself there. Okay, but I've stated that's what it is there. It's secondary, therefore the molecule is probably that.